In this video, we will be discussing about the data encryption standard, which is one of the algorithm used for symmetric cryptography. Now, data encryption standard algorithm is a very basic and standard algorithm, which is the basis of all algorithms used for the cryptographic purpose. Now, as we know that in symmetric key same key is being used for encryption and decryption, and we have many algorithms which are such as IDEA, DES, IDEA, RC5, Blowfish, AES. All these algorithms belongs to the category of symmetric cryptography. And this algorithm is quite popular, as well as the speed of encryption and decryption is also very good. And it is considered to be the basic algorithm for all kinds of cryptographic algorithm. So that is why it is necessary first to learn about the DES, and once you are able to understand how DES works, you will be able to understand the rest of the algorithm which will be used either in the symmetric cryptography or in the asymmetric cryptography. Now, this is the illustration of symmetric cryptography, in which the plain text is being converted by the use of symmetric key or the shared secret key to convert it into the ciphertext, which flows on the network, open network, and this ciphertext is being received by the receiver, which is being decrypted with the help of same symmetric key or the shared secret key to get the plain text by the receiver. Now, as far as the algorithm is concerned, that is data encryption standard, this algorithm is also known as data encryption algorithm, and this is considered to be the first algorithm and considered as a landmark in the cryptographic algorithm. And it generally it is used in ECB, CBC, and CFB mode, which we have already discussed in the video number 6. It is conceived in 1972 by an American standard company, and IBM has finally developed it. It is conceived in 1972, but it has come into the action in 1976. Of course, it is being developed by the IBM. Now, the DES is a little bit complicated algorithm, so you have to be very conscious about learning each and every steps, whatever is being used in DES. This is the conceptual view of DES. In this conceptual view, all the plain text, whatever the size of the plain text is, it is divided into a block. That is, the size of the block is 64-bit, and every 64-bit plain text block is being converted into the ciphertext block by the use of 64-bit key. Of course, here you will be seeing that we have written that it is 56-bit key. Of course, we will be in the very beginning we will be considering 64-bit key, which is later on converted or compressed into 60-bit key. So this 64-bit plain text is applied with the DES algorithm with the key which is of the size of 56-bit key to get the 64-bit ciphertext block 1. And similarly, all the plain text block is being encrypted by using DES algorithm using 56-bit key, and then we will be getting the different ciphertext blocks. Now, as I told you that initially we take the in original form as a 64-bit key, but later on we used to adopt a key discarding process by which the 64-bit block is converted into a 56-bit key, and the algorithm of doing the key discarding process is simply that every 8th bit is dropped. If every 8th bit is dropped out of the 64-bit, of course we will left with only 56-bit key. So this is the first process which we used to do, that we take the originally we take 64-bit key, and by using key discarding process we are able to get the 56-bit key. Now this is the broad level steps which are used in DES. Initially we take the plain text that is of 64-bit, and first of all we perform an initial permutation. Initial permutation is a kind of a technique by which, by using a certain table, we permutate the position of the bits. So by using a certain table, we permutate the bits of the plain text which is available in the form of 64-bit. And later on, the 64-bit, after doing the initial permutation, always remains 64-bit. Only the bit positions are going to be changed. And then we divide this, after doing the initial permutation, we divide the text, 64-bit text, into two parts. Each part is 32-bit, 32-bit. The left part is known as left plain text, and the right part is known as right plain text, and each LPT and RPT is of the size of 32-bit. Now this 32-bit LPT and RPT, then we apply key, and we apply key in the 16 rounds. We use 16 rounds on LPT and RPT with the help of the key, and after 16 rounds, whatever is the result, that is 64-bit. That 64 is again applied a table. That table is called final permutation. Again the bits are going to be changed, the bit position is going to be changed, and then after doing the final permutation, whatever text we will be getting, that is known as 64-bit ciphertext. So the total number of steps which are used in DES is to consider the plain text of 64-bit, apply initial permutation table to change the position of the bits, and then after doing that, convert into two parts, LPT and RPT, then apply the key for 16 rounds. And each round we will be using different key which is generated from the initial key. So after applying 16 rounds, we will be getting 64-bit text, and that 64-bit text is again using a final permutation table. We permutate the position of the bits, and finally we will be getting the ciphertext. So how it works, this is the general structure of the DES, in which we are taking the 64-bit plain text. After applying the initial permutation, then we will go for the round number 1, round number 2, and round number 3, round number 4, and we do round number 16. So 16 rounds we will be using 16 different keys. Of course, we have considered first 64-bit key. That 64-bit key is converted into a 56-bit key, and using a round key generator, for each round we are generating a separate key, and each key is of the size of 48-bit. So in the round number 1 we will be using K1, that is 48-bit key, which is generated by the 56-bit key. In round number 2 we will be using different key, that is K2, which is also of 48-bit, that is again generated by the 56-bit key, and so on. And then after doing the round operation 1, 2, 3 up to 16, whatever text we will be getting, we apply the final permutation, and after getting the final permutation, whatever text we will be getting, that will be the ciphertext, 64-bit ciphertext. This is how the initial permutation and the final permutation is steps. Now with the help, you can see the table. This is the initial permutation table which is applied in the very beginning. Now the first position, it is written 58. It means 58th bit of the plain text will become the first bit. Similarly, 50th bit will become the second bit. 42nd bit will become the third bit. 34th bit will be the fourth bit. 26th bit will be the fifth bit, and so on. So in this way we are we are doing the permutation process. That 58 bit will become 1, and so on. So this is how the initial permutation process used to happen. And what is the final permutation? After applying 16 rounds, whatever text we are getting, we apply the final permutation, and again the final permutation is done with the help of this table that is called final permutation table. With the help of this table, you can find that the 40th bit will become the first bit, 8th bit will become the second bit, and so on. So this is how the initial permutation and the final permutation is being done in the beginning. Initial permutation is done in the beginning process, and the final permutation is being done in the last process. This is how the round operation used to work. Now the round operation is applied on LPT and RPT. So this is 32-bit LPT and this is 32-bit RPT. So what we do, first of all, RPT is mixed in a mixture with the help of this key by a function fri-1, k1. It means with the help of this k1, this RPT is being functioned or mixed, and then it is being absorbed with L1, and whatever the result is, it will become the R1 for the next round, and whatever is the original RPT, that will become the LPT for the next round. So what happens in one round, the LPT and RPT is being processed, and with the help of K1 we process RPT, and then we mix it with the LPT, and whatever result, that will become the next round RPT, and the original RPT, previous RPT, will become the next LPT for the next round. Now this is the DS function. This DS function means whatever we are doing here, what we are doing here can be explained in this particular slide. That fr-1k, what is actually happening? We have an RPT that is of 32-bit. What we do, we expand that 32-bit using the expansion P box, permutation box. Expansion permutate 32-bit is expanded into a 48-bit. And we already know that for the round number 1, we have considered K1. K1 is of 48-bit. This 48-bit and this expanded 48-bit is being absorbed. So the resultant will be again a 48-bit. Now this 48-bit is divided into 6-bit format. So we will have, if 48-bit divided into 8 different blocks, so individual block will be having 6-bit, and each 6-bit is applied with the S box. For applying each block, we will be using separate S boxes. S box is nothing but, it is called substitution box. Substitution box is a kind of a box which is being designed by the IBM people, with the help of which the 6-bit, each block 6-bit is converted into 4-bit. And each 4-bit, and there are 8 such blocks, so the resultant will be 32-bit. And this 32-bit is again applied with the straight permutation box again to permutate the individual bits to get the 32-bit, and that will be the result. So this is the detail of the one round which happens in data encryption standard. The first one is the key transformation. Key transformation means for 16 rounds we are in requirement of 16 keys. So the 16 round, the 16 keys are being generated in this key transformation round. In expansion permutation, what we used to do, the RPT, which is of 32-bit, that is being expanded into a 48-bit. Now in this key transformation, what is being done? First of all, we will discuss key transformation. The original 64-bit key was previously converted into a 56-bit key. That 56-bit key is converted into different round keys, and each round keys is of the size of 48-bit. So for the 16 rounds, we will be generating 16 48-bit keys, K1, K2, K3 up to K16. And since key size is 48-bit and RPT is of only 32-bit, so in the second step, we used to do the expansion part of the RPT. And this RPT, which is of 32-bit, is converted into a 48-bit. And then this K1 is being absorbed with the RPT, expanded RPT. And then we apply the substitution box, then we apply the permutation box, then we apply XOR and swap. So all these 5 steps are being adopted in one round of DES. So first of all, we will discuss about the key transformation. What happens in key transformation? Now, as I told you that in the very beginning, we consider 64-bit key, which is being converted into a 56-bit key by discarding every 8th bit, and so we will be having 56-bit key is available. Now with the help of this 56-bit key, we generate a different 48-bit sub-keys for each round, and this is called the key transformation. So for this particular purpose, we will be considering 56-bit key, and what we do that 56-bit key is divided into two halves, each of the 28-bit, and these two halves are circularly shifted left either by 1 position or by 2 position, depending upon what kind of round it is. For example, if it is round number 1, the number shift will be done. If it is round number 1, so shifting is done 1 bit. If it is round number 2, shifting is done 1 bit. If it is round number 3, shifting is done 2 bit. So meaning thereby for every round we will be generating different keys. So only round number 1, round number 2, round number 9 and round number 16 are those rounds in which we are getting only single bit shifting. For the rest of the round we will be shifting 2 bit left side. So after doing the appropriate shifting of 48-bit, after doing the appropriate shifting of the 56-bit, out of that 56-bit, we select only the 48-bit. And for selecting 48-bit out of the 56-bit, we will be using this table, and this table is called permutation table or compression table. So what we will be doing, the original 56, if it is, suppose we have to find out the round key, that is key number 1, sub key for the round 1. So what we will do, we will take originally 56-bit key, we divide it into two parts, 28-bit, 28-bit, and each 28-bit keys, each 28-bit are shifted circularly, but since it is round number 1, by 1 bit left. So when it is circularly shifted 1 bit left, then we apply this compression permutation table to select only those bits and the size of that bit will be a 48-bit, because you consider 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So there are 12 columns and 4 rows, so we will be selecting only 12 into 4, that is 48-bit. For the second round, again we will be shifting the bits and then applying the compression table to get the K2. Again for the round number 3, we will be shifting 2 bit, and then now this shifting is being, it has to be considered that shifting whatever is done in the form of a 28-bit each, and whatever we are doing the circular shift, and after shifting we will be applying compression permutation for getting the 48-bit key. So this is how for the 16 round, the 16 sub keys of the size 48-bit are being generated. After this is the process of key transformation. Now the second one is the expansion permutation. Now expansion permutation is applied on the RPT. Why it is done on the RPT? Because RPT is of 32-bit. So whenever we have to work with the RPT, which is of 32-bit, and the key size which we have selected for each round is 48-bit, so why not to expand this 32-bit into a 48-bit, and the process of doing the expansion is called as expansion permutation. So what we do, we have original plain text that is of 32-bit. Each plain text of 32-bit we divide into 8 parts, and each block will be of 4-bit. Now this 4-bit is expanded into a 6-bit form. So previously there are 8 blocks, and 8 into 4, 32 was the original one, and each 4-bit block is expanded into 6-bit. So 32-bit can be converted into a 48-bit. So how it is being done? First we take the first block, that is 1, 2, 3, 4. So that 1, 2, 3, 4 has to be expanded into 1, 2, 3, 4, 5, 6. How it is being done? The first bit of the original one will become the second bit of the new one. Second bit will copy as it is to the third one. Third will be copy as it is to the fourth one. Fourth will be copied as it is to the fifth one. and the fourth one is again copied as the 7th bit, as well as the next block 5th bit is considered is copied into the 6th bit. So, and the first bit will be the last bit, that is 32 bit, that is the become the first bit. So what we do, we are doing the expansion as well as we are permutating. So each 4-bit block is converted into a 6-bit, and there are such 8 blocks. So 32-bit will be expanded and will become the 48-bit. So this is how the expansion permutation used to work. So the third process is the S-box substitution. But before going to S-box substitution, what we do, now we have key transformation, by which we have compressed the 56-bit key into a 48-bit key, and we were having expansion permutation process in which we have expanded the RPT from 32-bit to 48-bit. So we are now having 48-bit key and we are having 48-bit RPT. These two values are XORed together to get the that will become the input to the substitution box. So the resultant of the XOR operation will also be a 48-bit. Now how this substitution box used to work? The 48-bit input to the substitution box is converted into 8 blocks. Each block will be 6-bit of the size, and each 6-bit by using XBox1 will be converted into a 4-bit output. Since there are 8 such blocks, each block is of 6-bit, so we will be applying the individual S-box substitution box for the converting 6-bit sub-block into a 4-bit output. And for each block we will be using separate table. So S-box1 table is shown, for example, has been shown, and this is generated and designed and conceived by the IBM people, and as the book says that it took 17 man-years to design this S-box. So it is the IBM people who will be knowing about that, how they have designed this S-box, so that, because we don't have any idea, because they have designed in such a fashion that whether you are applying encryption or whether you are applying decryption, the same box will be used. But the purpose of using the S-box substitution is just to convert the 6-bit block into 4-bit. But we will apply S-box1 for the first block. Then we will apply S-box2 for the second block. We will apply S-box3 for the third block. And each S-box will be different from the one. So the first S-box has been shown, and we have left the rest of the S-box. Similarly, the S-box1, we have 7 more S-boxes. First S-box is applied for the first block, second S-box will be applied for the second block, third S-box will be applied for the third block, and so on. Since there are 8 sub-blocks, so we will be applying 8 such tables for converting the 6-bit value into a 4-bit value. Now how to use this S-box? This S-box is very simple. It has 16 columns and it has 4 rows. The the first row is considered as 0, 0. The second row is 0, 1. The third row is 1, 0. And the fourth row is 1, 0. The first column is 0, 0. The second column is 0, 1. And so on. So in this way, 0, 0, 0, 0 is the first column, 0, 0, 0, 1 is the second column, 0, 0, 1, 0 is the third column, and similarly the last column will be 1, 1, 1, 1. So how we are converting by applying this S-box 1, how we will be converting the S-box 6-bit block into a 4-bit, and for that this example has been shown. Now this example has 6-bit as the input. The 6-bit, out of that 6-bit, the middle 4-bit is considered as the column number, and the first and the last bit is considered as a 2-bit row number. For example, if we have an input as 1 0 1 1 0 1, it means the column value is 0 1 1 0 or 6 in the decimal, and the row value is 1 1. So what we do, the 6 in decimal, that is 0 1 1 0, 6 in decimal, and 1 1, that is decimal 3, the column and the row, wherever it coincides, whatever value of that, the equivalent binary will be the value. For example, if we take the same example, what will be the resultant? Suppose we are applying in the S box 1. So it is 6 in decimal as the column value and 3 in the decimal as the row value. Now let us go to the S box. Now this is row number 0, this is row number 1, this is row number 2, and this is row number 3. This is column number 0, column number 1, column number 2, 3, 4, 5, 6. So this is column number 6. One, two, 0, 1, 2, 3, 4, 5, 6. So this is column number 6. And this is row number 3. So wherever is the junction point? Junction point is 1. So the value is 1. So the output of this will be 4-bit number that is equivalent to the 1 binary. And the 1 binary equivalent 4-bit number is 0001. So in this way, we will be applying the S box value, and we try to find out which column value, which column number, and which row number, and whatever is the wherever it coincides and whatever value has been placed in that particular box, we consider the binary equivalent of that value, and that will be the 4-bit equivalent to the 6-bit. So this is how the S box substitution used to work. Then we have P box permutation. So let us go back. So what we have done key transformation. We have learned about the expansion permutation. We have learned about the S box substitution. And now the 4th step in one round is the P box permutation. So the P box permutation, we apply the output of X box consists of 32-bit. Why it is 32-bit? Because 4, 4, 4 and 4-bit each block, and there are 8 such blocks, so the resultant will be the 32-bit. So this 32-bit is again permutated. The position of the bits are going to be changed, so that 16-bit will become the first bit, 7th bit will become the second bit, and so on. So we apply the permutation box. And the last step in the round method is the XOR and the swap. Now this is the general description of XOR and swap. Originally we have 64-bit plain text. That 64-bit plain text, after doing the initial permutation, we divided into 2 parts, LPT and RPT. And for RPT, what we are doing, after considering it as LPT and RPT both of 32-bit, first of all we will do the key transformation. Then we will do expansion permutation on this RPT. Then we apply S box substitution on this RPT. Then we apply the P box permutation, and then whatever is the resultant is XORed with the LPT. And whatever is the final value, that will become the 32-bit right plain text. RPT will for the next round, and the original RPT will become the new LPT for the next round. So this is how the XOR and the swapping is being done. So if you try to understand the each steps, whatever is happening in the round, each round, the first is the key transformation to achieve the key. For the round number 1, you will be getting K1. After that, whatever is the RPT, it is being expanded. Whatever is the RPT, after doing the expansion, we XOR the RPT with the help of the key 1. So whatever is the result, that will be 48-bit. That 48-bit is applied to the S box to get 32-bit. That 32-bit is permutated using P box permutation. And after getting 32-bit output, that is being XORed with the original LPT to get the new RPT. And the original RPT or the previous RPT will become the new LPT. And this value will be going into the next round. In the next round, what happens? Again, we try to find out K2 by using the key transformation process. Again, whatever is our RPT, we used to expand it into 48-bit, and then K2 is being XORed with the expended RPT, and after that S box substitution is applied, and then P box permutation is applied, and then it is being XORed with the LPT of that, so that to get the new RPT, and then the previous RPT will become the new LPT, and this process goes on up till the 16th round. So all 16 round, all this thing happen, that you have to transform the key, you have to take the RPT, you have to expend it, and then you have to XOR with the key, then you have to apply the S box substitution, then you have to apply the P box permutation, and then XOR with the LPT to get the new RPT, and the 32-bit RPT will become the new LPT, and this process goes on for all the 16 rounds. And after doing all these 16 rounds, after doing the 16 round operation, you have the final permutation. Of course, the final permutation has been already I have given the idea of the 16 round final permutation, that the bits positions are going to be changed, and in this way the final permutation used to this table and the table which has been shown earlier with the help initially with the initial permutation same. So the final permutation is being done on the 64-bit, and after doing the final permutation, whatever is the resultant, that result is known as ciphertext. Now this is how you are applying DES algorithm on the first block of the plain text. Similarly, you have to apply the DES for all the blocks individually. So this is how the encryption process of DES used to work. Now, the decryption. This is how encryption is being done. Now the decryption. Now, the algorithm which I have discussed till now, it seems to be very complicated. Yes, of course it is complicated, but if you try to learn it very carefully, it can be understood very easily, and it can be implemented by the certain program onto the computer set, so that you can do the encryption by using the DES. The process is very simple. Let me give you the top to bottom approach, that is the step number 1, 2, 3, 4, 5, 6, and how DES used to work. I am just repeating the process. Whatever the plain text size is, it is divided into 64-bit blocks. Each block is being applied with the DES algorithm with the help of key. Initially, we take 64-bit key. Later on, by key compression table, we compress the 64-bit key to 56-bit key. And after that, 64-bit plain text is being initially permutated by using a table. And whatever is the resultant is divided into LPT and RPT. And then LPT and RPT goes into the round. And there are 16 such rounds. In round number 1, what happens? We generate a subkey of 48-bit from the 56-bit key by using a certain process. And then we expand the RPT from 32-bit to the 48-bit. Then we XOR the RPT with the help of key to get the 48-bit resultant. Then we apply S box substitution to get 32-bit again. Then we apply the P box permutation so that the bits position will be permutated, changed. And then we XOR the LPT with the resultant to get the new RPT, and the previous RPT will become the new LPT. And then we will go into the next round. And in this way, after doing it in the 16 rounds process, then we apply the final permutation table to get the ciphertext. So, of course, DS seems to be complicated, but the same algorithm is applied for the decryption also. Same algorithm, nothing will be changed. But there are certain process which is required to be changed. Now, while designing the DES, it has been considered, it has been taken care that all the tables and as well as all the operations are so carefully chosen that algorithm is reversible. Whatever you are doing for the encryption, the same thing you will be doing for the decryption also. The only difference which lies is the reversal of the key position. While doing the encryption, we will be applying K1 first key, K2 second key, K3 third key, K4, K5, K6, K16. But while doing the decryption, the process of applying the key is going to be reversed. That while doing the decryption, you have to consider only K16, K15, K1, but rest of the process will remain same. All the tables, whatever you are using as an initial permutation, whatever you are using a final permutation, whatever you are using as a P-box permutation, whatever you are using as a S-box substitution, whatever table you are using, all the table will remain the same, all the steps will remain the same, but the only difference lies in applying the key. While doing encryption, we start from K1 up to K16, but while doing the decryption, we will apply K16 from K16 to K1. And the second difference is, of course, the plain text is the input in case of encryption, but ciphertext will be the input in case of the decryption. And the rest of the process, tables, as well as the sequence of the operation, all the things remain same. So no need to discuss in detail about the DES description. This is the only part which I want to mention here, that the reversal of the key is being used while doing the decryption process in comparison to the encryption. Now, as far as the strength of the DES is concerned, there are basically two important strengths of the DES. The first one is the key size, because you have seen in the last video that I have shown that if the key length is more and more and more, it is difficult to crack the key. So that is why, since DES uses 64-bit key, so it is quite safe, because if it is 64-bit key, which is further reduced to 56-bit key, so considering only 56-bit key is being used in the DES, this means 2 to the power 56 possible keys. So as far as the brute force attacks is concerned, it seems to be impractical. Of course, nowadays nothing is impossible. It can be done, but still this is safe. The second important strength of the DES is the use of S-box. As I told you earlier also, that IBM has kept it secret. Why it has been designed in such a manner? It is the people who have designed it know that why the first bit is 40th bit, second bit is 10th, and so on. So IBM has kept it secret as S-box substitution, and it took over 17% years to come up with the internal design of the S-box. And it is very difficult to crack, because S-box is designed in such a manner that whether you are applying encryption, whether you are applying decryption, the result you will be getting the same. So same box is applied for the encryption process as well as the decryption process, and it is very difficult to crack the S-box. Why it has been chosen in such a manner? This is known to the people only, and still it is uncracked. But even though as the time and the development has been done, and more sophisticated and the more and more powerful computer has come into the picture, so people come with the idea that 56-bit key is not more than sufficient. So we have to strengthen DES more and more so that it should remain uncrackable. So the other versions of DES has come into the picture, and that is known as modified version of DES. And this modified version of DES has 3 versions. First is double DES, in which the DES is performed twice with the 2 different key. Second one is triple DES with the 3 different key. And third one is the triple DES with the 2 different key. Let us see what is double DES. This is a very simple process. We take the original plain text, and instead of using only one key, we will be using 2 different keys, each of the 56-bit, to encrypt the original plain text. So we take the original plain text, apply the key K1 to encrypt into the ciphertext. This ciphertext is not sent to the receiver. Again, this ciphertext is encrypted by using 2 keys. That is why the name double DES has been used, because we are using 2 different keys, K1 and K2. And of course, while applying the DES, K1 is being converted into 16 different keys, and K2 will be again into 16 different subkeys. So K1 is applied to encrypt to get the ciphertext, and this ciphertext is again encrypted by the second key to get the ciphertext. And this ciphertext is the final ciphertext which has to be sent to the receiver. This is how the encryption process the decryption process is same. So whatever ciphertext we have received by the receiver, it will apply first K2 to decrypt it to get the ciphertext, and again this ciphertext is being applied with the K1 key to decrypt it to get the original plain text. But double DS is having a certain problem. There is called meet in the middle attack, which comes into the double DS. And how it happens? Now, as far as the mathematical expressions are concerned regarding the DES, the plain text P is encrypted by K1. E stands for encryption, K1 stands for K1 key, P stands for the plain text. So, whatever result we will getting EK1P. And this T is equal to EK1P is further encrypted with the K2 key. So, it will be EK2 in the bracket EK1P, and then C will be equal to EK2 bracket EK1P. So this is the final ciphertext. So, but double DS has a certain problem, and that is called, I was discussing about the meet in the middle attack. If if any attacker is able to know about the plain text, and he also knows the ciphertext because ciphertext is running. So what he will do? He will encrypt with the if he knows the plain text. So it will encrypt the K1 to get the plain text. It will encrypt the P with the help of K1, a certain key K1, to encrypt the process to get the temporary result. If he also knows C, and it decrypts that C by the help of K2 to get another T. And the time will come when both the T will be equal, he will be able to know what is the value of K1 and what is the value of K2. Meaning P is encrypted by a brute force attack by using a certain key to get the temporary result. C is decrypted by K2 to get another result, and if both the results are going to match, it means the value of K1 and K2 has been found. So double DS is not very popular. So the people come with the idea with the triple DS. Why not to use 3 keys? 3 times why not we are doing DES operation on the plain text by using a simple process that we take the original plain text, apply K1 to encrypt to get the ciphertext, apply K2 key to again encrypt the ciphertext 1 to get the ciphertext 2, and again apply K3 key to on the ciphertext 2 to encrypt it to get the final ciphertext. But it seems to be very tedious job to use 3 keys for one operation. So another modification which has been made in the triple DS, that why not to do use the triple DS with the 2 keys. So the first key we will be using, instead of 3 keys, we will be using 2 keys only. Original plain text is encrypted by K1, and then ciphertext is being decrypted by K2, so that to get the ciphertext 2, and then again ciphertext 2 is encrypted by K1 to get the final ciphertext. So this is a little bit more safe, easy, and less number of keys. Instead of 3 keys, you will be using only 2 keys. That's all from this side.